Contact information, because it's pretty easy. You saw what I had set up, right? So, like I said, I think me picturing a picture is kind of, I hope. That could be really annoying. Watch this. There. I don't know. That's better. Okay. So, Le Chateliers principle, what is it? Other than sounding kind of French, right? So according to Le Chateliers principle, it deals with systems that are in equilibrium. So you have kind of reactants going to form products, a two-way arrow, the products are going back to form reactants, okay? So Le Chateliers principle needs a chemical equilibrium. So basically, Le Chateliers principle talks about a stress, and you can think of it as kind of a poke. Okay, so you basically have a system minding its own business, going back and forth between reactants and products according to its equilibrium constant expression, and you poke it. That's Le Chateliers principle. That's the stress. Okay, so depending, and we're going to talk about different stresses, but depending upon how you poke it, okay, your equilibrium is going to respond. So this definition kind of implies that it will be out of equilibrium for a little while, and it will. Okay, it's going to have to establish, it's going to basically not start over, but have to kind of do a little rethinking the reactants and products that it has at equilibrium. It's almost like it has mind, its own intelligence. Maybe not. Okay, so how do you poke it? How do you stress it? A system that's in equilibrium, here are 4 general ways that you can poke it. Okay, you can sprinkle a little bit of reactant or product in it. You can remove a little bit of reactant or product. That's the first one. You can monkey with the thermostat, change the temperature, see it sweat. You can change the pressure. And actually, we are going to, in this part, actually talk also about changing the volume. So especially if everything's a gas, think of those. We definitely have some chemical equilibria where all reactants and all products are gases. Think about changing the volume, and it's going to have consequences. It's going to be out of equilibrium for a little while. It's going to reach a new equilibrium. I'll kind of show you what that looks like. All right. That. All right. So I'm going to go ahead and write this up here because I'm going to be referring to it. It's got like 4 over here. It's like somebody, so do these work or don't work? And they've got like 4 over there. So we've been talking for a while. Well, you can have 2 reactants and back and forth forming 2 products. And we said the stoichiometric coefficients are actually what's going to show up as superscripts, exponents, in our equilibrium constant expression. So the equilibrium constant, Kc, is equal to the molar concentration of the products raised to their stoichiometric coefficients divided by the molar concentration of the reactants. Cool. Well, let's talk about stressing it. By the way, so we talked about a reaction quotient expression, which looks exactly like your equilibrium constant expression. But this is the snapshot, remember? I've been talking about. And this is specifically at equilibrium. So here we go. Let's think about... Okay. Let's try this one. The first line of poking equilibrium, we said you could add or subtract reactant or products. So let's go ahead and stress the equilibrium, and we are going to add A. We're going to sprinkle some more of one of the reactants in there. Okay, first off, if you sprinkle a little bit of A in there, do you guys buy this? That actually, you know, you could go ahead and calculate your QC, and your reaction quotient now is not going to be equal to your Kc. Okay, it's going to be what? too small. Does that make sense? If we increase this down here, you're increasing the denominator, and that will decrease your Kc. And one of the things that we talked about earlier, that if your reaction quotient, your snapshot, is smaller than your equilibrium constant Kc, then that means that you don't have enough products. So we would say that the result of stressing that equilibrium by adding A is to force it to form products. That's how that goes. Okay. So reactants must be converted to form products and to reach a new equilibrium. But mathematically, when the dust settles, you got to get back to your equilibrium constant Kc. So a whole list of things happen. By the way, can you almost see where where this is kind of like a push? Okay, so literally, this is a push. It increases this. So you can kind of think of a number of things happening. If that's the case, then just by stressing the system, by adding more A, you automatically, with the new equilibrium, will form more C and D. These are all kind of, and actually we're going to do a Kahoot at the end of today. It's going to be a survey form, not the whole points thing format. But in our Kahoot, I'm going to be kind of asking you these kind of little brain teaser sort of things. So if it's going that way, you're going to form more C and D. You're going to have less A. Oh, wait a minute, sorry. You're going to have greater A because you added A. Okay, but you're going to have less B because you didn't add any B. Okay. So that's how that works. But bottom line, like I said, mathematically, when the dust settles and you're at a new equilibrium, it's a new equilibrium, but the same old new equilibrium concentrations, but the same old Kc. So mathematically, it's got to kind of fix itself. That is so cool. Okay. Let's look at another one. Say a similar idea, but instead of adding A, let's subtract A. Okay, so if we take some of this out, okay, notice what's going to happen is you're going to have less in the denominator, so your numerator is going to be too big, basically. Okay, less here, the numerator's too big, so what has to happen is those need to get less. Another way to look at it is if your concentration of A decreases, then that will make your reaction quotient, your QC, larger than your Kc. And we said if it's too large, then we have too much products, so basically it has to come back this way. So one of the things I say, if you're taking out something, it's kind of like you're pulling it. If you're adding something, it's kind of like you're pushing it. Okay, so we're taking out A, so we're pulling it along. Okay. So consequences are this. At your new equilibrium, your products are going to be less at your new equilibrium because you stressed it in that way. So C and D will be less, A will be less, and what do you think about B? Greater, very good, you got it. A will be less, and B will be greater. Perfect. And then I have just one little caveat down there at the bottom. So your equilibrium concentrations will change, okay, but they have to be mathematically at equilibrium equal to Kc when you plug them into the equilibrium constant expression. Very cool. And I'll warn you that there are some ways to stress. I'm going to try to kind of spell out how this works, but there are some ways to stress an equilibrium other than adding or subtracting, in this case, a reactant, that actually you'll get a new Kc. You do not need a new Kc here. So at the end of this lecture, there's one slide that has an equilibrium, and actually that's our Kahoot at the end, right before your assignment slide. And so I'll kind of quiz you over that. But I could have, instead of picking on A, I could have picked on a product and kind of done those same two things, adding a product or removing a product. So, all right. So I mentioned some stresses to systems you get a new KC. This is one of them. So somewhere in your putting pieces together, know that if you change the temperature by adding or subtracting heat, warming it up, add heat, cool it down, subtract heat, then you're going to get a new equilibrium constant expression. Those problems we've been working, a lot of times they'll give the temperature. We haven't been using the temperature, okay, but the KC is specific for a temperature, and that's why they do that. So which way does it go? Okay, well that's what I kind of need to explain. I need to go back to what we talked about, and we've been talking about in chemistry, the whole endothermic and exothermic reactions. Well, there are endothermic and exothermic equilibria too. So if we start with an endothermic equilibrium, if it's endothermic, I bet you guys buy this. If it's endothermic, I'm going to put heat on the reactant side. Okay. So here's the deal. If I add heat, does that seem like, can you almost see it pushing? If I add heat. And that's really kind of the deal of it. If I add heat, I'm going to encourage or promote the formation of my products, which are C and D. So adding heat to endothermic reactions, that's what happens. Okay, if you kind of think of it like that, that should work for you. Okay. So at the higher temperature, and now this isn't, you get a new KC, like I tried to say. You don't have the old KC. So at the higher temperature, okay, you're going to favor products, favor P, products, and where are products in your equilibrium constant expression? They're in the numerator. Okay, so that's why your equilibrium constant is higher. Endothermic though, that's it. And if you kind of, there's a lot of things in physical science that I don't memorize, and this is probably one of them. Every year when I get to this, I think through it. So I do not memorize endothermic, higher KC if you add heat. Because here's one for you. What if we remove heat and it's endothermic? It's not a push anymore. It's a pull. Okay, if it's endothermic and we remove heat, okay, guess what? It's going to actually, we're going to favor the formation of our reactants now. So at the lower temperature, we have more reactants. So at the lower temperature, it's going to be a lower KC. Okay, so it still works. All right. Next scenario. So something with and by the way, I won't say they're endothermic or exothermic, but I will simply give you the heat of the reaction, the delta H, and you guys know if it's negative, it's exothermic, and if it's positive, it's endothermic. So you're going to need to remember that for your homework and for your test and such. So if it's exothermic, we can put heat on the product side. Okay, so now if we increase the temperature, okay, it's like a push, okay. So actually increasing the temperature will have a new equilibrium constant, and that new equilibrium constant will favor the reactant side. Okay, increasing the temperature will favor the reactant side if it's exothermic. So if it favors the reactant side, the reactants are in the denominator. So if they get larger, then the KC gets smaller. Okay, so that's why down here, when you get your new KC, okay, it's smaller than your before you added heat. Okay, so again, you guys don't get a note card for your unit exams in here. You do for your final. Okay, but you're going to want to kind of make that work for you. These inequalities are the opposite for each other, endothermic and exothermic. All right. Another way to shock the system, if everything, well, I guess not everything has to be in its gaseous state, but anyway, is to change the volume. Now, we assume in this case that everything is in its gaseous state. So let's see what works there. And I'm going to kind of show you a little proof to kind of get to the conclusion that I'm going to show you. It's really kind of even though the proof looks a little hairy, the conclusion is just a really kind of straightforward sort of thing. So we could express the molarity of anything as the number of moles divided by volume, okay? And the cool thing about these gases is basically they're banging around in a common volume, so we're going to make use of that. So we can actually go ahead and substitute out those molar concentrations for the moles of the products, okay, divided by volume. All in each case raised to their stoichiometric coefficients. So don't lose track of what the little c and d and the little a and b mean, okay? Those are stoichiometric coefficients. Well, we can pull out the volume term, because actually that's what we're interested in, because we're going to change the volume and see what consequence it has to the equilibrium. And it looks like this, where we pull out all the volume terms, leave it as 1 over v, and then go ahead and bring in the exponents. Again, these are coefficients, stoichiometric coefficients. So it's c plus d minus a plus b, because they're in the denominator. So 1 over v. Well, we're not quite done manipulating it, because we want to go ahead and get that 1 over v. We want to kind of clean that up, just make it just volume instead of the inverse of volume. So if we do that, notice the difference here is we have swapped those to go ahead and to kind of clean up the inverse sort of thing. So now instead of the sum of the stoichiometric coefficients of the products minus the sum of the stoichiometric coefficients of the reactants, now it's the sum of the stoichiometric coefficients of the reactants, those are these, minus these, okay? So v is raised to that power. So one last thing before I kind of finish talking about this. The only thing I've done here is replace the equilibrium constant Kc with that reaction quotient, QC. And I did that this afternoon because I was like, I always get to this part and I'm like, now shouldn't that be a snapshot? And yes, it really should. Okay, so we can take a snapshot of what your equilibrium is doing by looking at the moles, the individual moles raised to stoichiometric coefficient. But my point here is that it's times V, and this is what we're going to change. Okay, so here's how it goes then. If we're monkeying with the volume, I'll put these up here. And let's just say we're going to increase the volume, just for kicks. We can talk about decreasing the volume later. But if we increase the volume, and if its exponent is positive, okay, then, if we increase the volume, there's this too. If that exponent is positive, then we increase QC, then we have too many products, and you have to go back in order to reactants in order to reach equilibrium. See, I'm like, I just want to get to the next slide that summarizes it. Okay, so if this is positive, okay, then we have this scenario. Basically, it ends up being larger than your QC, and you have too much products, so you need to go back and form reactants. If this is negative, then anytime you take something raised to a negative exponent, basically that's a fraction, okay? And then what's going to happen is you need to go to, it makes your QC smaller than your KC, and you need to go to form products in order to reach KC again. Bottom line is this. I told you it was pretty straightforward. We are actually on either side of the equilibrium arrow. We are going to count moles of gas by looking at their stoichiometric coefficients. And if you increase the volume, this kind of makes, I like this because I can almost see that. If you increase the volume, then basically, I'm going to put it this way. I usually say more moles. Well, I guess it should be most moles. Whichever side has the most moles is what's going to be favored. That's it. By increasing the volume. So what do you think? Decreasing the volume is the opposite. So decreasing the volume is going to favor the smaller number of moles. So if you ever hear me say most moles, that's what I'm talking about. So let's look at a couple of examples. All right, so can you see this where if we add up moles on the reactant side, 2 plus 1 is 3. That's where the 3 moles came from. The coefficient for the O2 is 1. And then over here on the product side, we just have 2. Okay. So increasing the volume would favor the reactant side. Exactly. So if your volume was increased, your H2O would be converted back to H2 and O2. Now in this one, we're back to the same situation when we added more reactant or subtracted reactant. Your Kc is the same. Your Kc holds constant. The only time the Kc changes is with temperature. So yeah, think of when you decrease volume, it favors the fewer moles, which in this case is the product. So decreasing volume would make it go back, or excuse me, would make it what we say forward actually. Is that right? I think so. So this is actually going to kind of be kind of a proof to talk us through changing the volume. I think it's a cool idea. It also kind of gets us thinking about some other things. So first off, though, make sure we know what we're doing here. Okay. We are going to actually double this volume. You're going to see here in a minute. So do you buy this, that we have 4 moles over here versus 2 moles over here? If we increase the volume, which way does it go? Yep. If you increase the volume, it's going to go that way. Exactly. But let's kind of prove it to ourselves. So these are equilibrium concentrations that actually, if you plug into your equilibrium constant expression, you will get the Kc for this at a particular temperature of interest. Okay. So this is a good example. Actually, the Kc was not yet given to us. And you guys have had some experience at this, to go ahead and take those 3 equilibrium concentrations, to plug them back into your equilibrium constant expression to knock out Kc. So it's your ammonia concentration squared divided by your nitrogen raised to the 1st power, also in the denominator your hydrogen raised to the 3rd power. Rounding it to 3 sig figs, okay, so that's your Kc. Must already have that? Good. All right. So I mentioned doubling, so we're going to double this container. They're all gases, and they're going to fill up the container. And you would think maybe that they would keep the same equilibrium concentrations, but they don't. But they keep the Kc because we didn't change the temperature. Okay? So, let's see. So like I said, if somebody says, I have this equilibrium and I'm going to change the volume. If I want to know which direction the equilibrium is going to go, well, you just look at the number of moles on either side of the reaction arrow. So we've got 4 to 2, and so you guys told me it's going to go back and form reactants. So in order to kind of think through this, let's go ahead and come up with, I'll put all 3 of these up here. That 2, by the way, is just because we doubled the volume. So if we doubled the volume, then we have half the molar concentration. So I would put little subscripts, zeros here. Okay? Because we stressed that system, and we have these concentrations now, but they aren't at equilibrium. I'm going to prove that to you, that these aren't equilibrium concentrations, because all we need to do is basically plug them back into our expression to see if we get Kc, and we won't. Because, like I said, if you're like me, you're like, hey, those are still equilibrium concentrations. No, they're not, because you doubled the volume. Okay, so we're going to plug these into a reaction quotient expression and see what we get. Okay, which looks exactly like an equilibrium constant expression, right? But here's our snapshot. So these were our new diluted molarities. Ammonia now is 0.0790 squared. Nitrogen is 0.461 raised to the first power. And the hydrogen's 0.387 raised to the third power. So if we work that out, round it to 3 sig figs, you'll get your QC is 0.243. So right away, you know, the fact that your snapshot is not equal to your equilibrium constant, you know, it's not at equilibrium. And we said if your QC is too big, we said that you need to get rid of some of your products, right? And go back to form reactants. And actually that's what we anticipated. We said it would favor the formation of the side that has more moles. And so actually we've kind of come a little bit full circle here. So that was a little proof to kind of show you that we are on the right track. Nice, neat, and tidy. Okay. Is this the one? What's your notes look like? Oh, good. Okay, yep. This is it. Okay. So get out your, you didn't hear us talking, Andrew, at the beginning. We're going to do another Kahoot, but it's going to be a little bit different. I think we're going to like it. So go to Kahoot.it. Math is going to be so sad he misses. Oh my gosh. And I need to give you a, to log in, you're going to want this 6-digit code. Oh, you see it, little caution, your high CPU usage is affecting the meeting quality. So what's new? Okay, so 403781. And I think it still asks you for a name, but it'll be a little different than last time. And we need to make that music stop. Zzz. I need one more player. I lost one player. Andrew, oh, that's real obvious. And Lexi, that's real obvious too.
Yeah, yours are fine. Jeez.
By deduction, right? Okay, so I did go ahead and make these, I think 3 minutes if we want it. But here's what it's going to look like. You see the question, the last 2 slides, right? The last 2 slides basically give you a chemical equilibrium. Is it endo or exothermic? What do you think? Does it give you delta H? Is it positive or negative? It's endothermic? Okay, very good. That's going to be a player. And you already see kind of the questions, no pun intended. You see kind of the questions that it's going to ask you. So there are 6 quiz questions. and it's gonna ask you those questions. But like I said, haven't installed the right or the wrong answers, but we're gonna look at that endothermic equilibrium, and we're gonna ask some questions, kind of like that would be on your homework and on your test.
Do you mean this is our homework for the weekend? Okay.
No, sorry. Okay, so you kind of, I guess it's only a minute and a half, but you're fine, you're among friends. So here's your equilibrium. You guys told me it's endothermic. The first question is, what if you add, which has nothing to do with endothermic, what if you add more N2O3? Okay, what will happen with your NO? If you add more of this, will your NO increase, will your NO decrease, or will there be no effect on your NO if you add more N2O3? And it goes on to, and we're showing NO would increase. Sorry. Okay. Whoever said increase, can you kind of explain why it would increase? Because you're right. In your own words. Come on, this is peer tutoring. I'm going to put this up here. So can someone tell me what that
Oh my gosh,
equilibrium
it kicked
is?
me out.
Did it? Because why?
That's so mean.
I think, are you on your own 3G or on the?
I'm just on my own network.
That's why it does it, because I did Wi-Fi this time.
Ah.
So for your Wi-Fi.
Yeah.
Okay. So N2O3, we have one reactant, everything's in its gaseous state. Okay, one reactant goes to form NO. And this is actually, all of the questions asked what effect it's gonna have on the NO. And, oh, there's all 1 moles of everything. NO2 gas. And delta H is equal to plus 40.5 kilojoules per mole. Cool. I'll put a question mark here, so this is the question. So, if you add more if you add more of this, kind of think of it as pushing. And actually, it works out in your KC expression too. NO, molar concentration at NO2, all raised to the first power, right? Molar concentration N2O3. You know, if you're one of these also, if you kind of think of it this way, if you add more of this, okay, then actually it's going to have to equal out. You're going to have to form, this is going to have to be converted to this in order to keep this constant. Andrew.
You asked us to explain it in our own words. One way I thought about looking at it is, since it's at equilibrium, it's basically that's an equal sign, the reaction arrows.
Okay.
So that if N2O3 was a number, say 10, and that was 5 plus 5, and the 10 went up, then one of those numbers would have to go up in order for it to equal.
Do you see what he's saying? Yeah, I like that.
Yeah, that made
Very good. Thanks. Well, thank you. Let's go on to the next one and hold
What's
that
your
thought.
game pin?
Oh, what's the game pin?
Yeah.
Is it at the top?
403781.
40371. Okay.
Did we get you back?
Yeah.
Oh, okay. Next one. Very good. Thanks, guys. Okay, now this one's changed. It says adding more NO. Adding more NO. What's that going to do to the NO concentration? Seems kind of a strange question. Okay, adding more NO. Are you going to increase your NO at equilibrium? Adding NO, the new equilibrium. We have more of this, we have less of this, or will this stay the same? And it's kind of like the A when we started with A today. Did you almost fall out of your chair? Okay, so let's see, the answer is actually you'll have more. So it will increase your NO. I know it seems kind of strange. Adding more NO will increase your NO at the new equilibrium. So can anybody explain that one?
No, I got it wrong.
Okay, well, it just does. How's that? Let's go on to the next one.
What's the game pen again?
Game pin?
4, what?
03781.
Okay, got it.
This could be a commercial. Okay, next one. What if you remove some of this, and I think that, you know, what if you remove this, let's go back to Andrew's thing. What if you remove some of this? What if you make this smaller? What's gonna have to happen to NO? Oh, very good. All right, I'm liking it. Next one. What happens if you increase the volume of the reaction flask? Increase the volume of the reaction flask. Increase the volume of the reaction flask. What's going to happen to NO? Very good. Wait. Increase the volume. Actually, it will increase. So let me explain this one. It favors the, increasing will favor the side that has more moles. More moles is on the product side, and it was a product. Nice guess, though. Do you buy? I don't know. You don't look sold on that. That's the way that works. Okay.
I was just confused because when we increased the volume earlier, but it was for the molarity, so that's where I sort of think decrease. 'Cause
Okay.
That's what I was thinking too, would be a smaller movement.
So that's where I was like looking at you like trying.
Oh yeah. That was a little side proof. That
Yeah,
actually.
that didn't really have anything to do
Well, I sure didn't mean to mess people up by doing it. It's a little proof, yeah. Yep. So forget the proof now and just focus on the thing or the bottom line. Good. Okay. Lowering the temperature. Lowering the temperature. And actually, this is one. Like I told you, I always think through it. I did not memorize those inequalities. It is endothermic, right? So it's the first example we talked about, changing temperatures. And so if you lower the temperature, at a lower temperature, you're going to have a different Kc value. If you have a different Kc value, okay, think of your new Kc, whether it's higher or lower, and then think of what consequence you'll have for NO. It's like a stepwise process. Hey, that should work. If I put energy over here, I'm cooling it down. Okay? So guess what? Yes, I say decrease. Very good. And it's weird to think you get a new Kc, so you have, it does definitely affect it. Good, okay, that works. All right, increasing the total gas pressure inside the flask by adding helium. I think this is the first one, or excuse me, the last one. So I have a box here that has those three things in equilibrium, two reactants, and one reactant and two products. They're all going kind of back and forth. What if I inject a fourth gas, and it's helium? And now I have helium gas particles bouncing around in the same container. And I don't think I've talked about this yet, but it's a good one to get under your belt. Do you think, does it change the molarity of anything? Does it change any of these molarities? No effect is correct. Very good. So I think that's kind of all this will do. We're all winners, right? There's no winners, losers. I kind of like that survey thing. Okay. So let's take a look at your homework. Did you guys want to see those slides so you can fill those in? Let's see. If you do, this is what that looked like. Oops, sorry, dang. Do you guys need to fill those in? Are you okay?
I did that.
Yeah.
Okay, good. All right. So the homework, dun dun dun. Yeah, you wish that was our homework. But I don't think I have a whole lot to say about the homework. Let's see.
That could be bad.
Ah. No, I think it's okay. They look like this. So, for instance, this is your first of 4. Chemical equilibrium. Explain how. It's like we did with that little quiz thing. You know, it's after you talk about Le Chateliers principle. Well, how does stressing it affect something? In this case, they're all after the H2 gas. So basically, we have some stresses here, A through D, and what happens to your H2. That's it. What happens to your H2? So I have a few hints here. My first hint is there's nothing, you can't go wrong with writing the equilibrium constant expression. You're like, why would I do that? Well, if you do that, then you start to kind of, things fall out like, notice that those 2 solids, they don't appear in your equilibrium constant expression. If you change the concentration of those or whatever, it's not going to affect your equilibrium, okay? So the first stress is monkeying with the temperature, and you're going to want to look back in your notes. But I really like this, you know, since it's exothermic, okay, exothermic, we would heat over here, right? And the thing is, what if we raise the temperature, so you jack more temperature in, so what's that going to do to your hydrogen, okay? So if you jack more temperature, it's going to make this go this way. So does it seem, I'll go ahead and tell you, but does it seem like your hydrogen will go down? Because it will. If you put heat over here, I keep pointing up here. Oops, darn it, go back. If you put heat on the product side, where to go? Ooh. So all I was trying to say was, if you put heat over here, okay, and the question is if you increase the temperature, so if you add heat, okay, it's like pushing it this way. And you have to think through it if you're like me. If you're pushing it that way, can you see where your H2 is going to become less? That is true. Okay. Or you can go back to the notes. But that's what will happen. You don't look convinced about that one either. Okay. Take a look at B. You're adding a reactant. Okay. What if you're adding H2O? How many people think you'll get more H2? 1, 2, yeah. Yeah. So exactly. C says you're going to double the volume. Okay, so ignore the Fe and Fe3O4. Increase in the volume favors more moles. How many people think, oh my gosh, they're the same? So, no effect. I'm kind of liking it. I get excited, right? The last one, I'm glad to mention this because I usually have to kind of remind myself how this works. The last one talks about a catalyst. And I didn't talk about a catalyst in Le Chateliers' principle lecture. And we talked about a catalyst when we talked about mechanisms and things going faster. So honestly, it's only going to make the equilibrium kind of establish itself more quickly. No effect. Okay. Very similar to the previous one. E, that's like your helium. Okay? It actually is helium, isn't it? Basically, adding another gas in there, it's just like, they all bounce around together. Doesn't change your molarities. Now, all of these are increasing the volume. Okay, so look for the more moles, but watch out for those solids. Okay, that was my hint. Okay, in each case, let's see, what effect? I think, and I didn't say it yet, but I think what they're after is, let's see, say forms more product or more reactant. That's what they're after. So you have 50-50 chance, but look for the more moles. say if it forms, say if it forms. All right, so the last one, notice you're given the enthalpies for the reaction. We have an exo, an endo, an exo, and an endothermic. And notice you're going to increase the temperature in each case, okay? And again, well, in this case, they're saying the forward reaction, let's see, would you expect the forward reaction to increase? So, yes or no? Okay, because it does say explain. All right, so not too bad.
Mrs. Snipes, do you want our homework?
I do want your homework. Thank you.